All right, let's talk about this first question here. The shape of the periodic table, what's it based on? Say again?
Electrons?
Nope. Who came up with the shape of the table? Or who came up with the table? Mendeleev, Dmitri Mendeleev. Did he believe in electrons? Nope. So it wasn't based on the shape of the container. Not protons. Reactivity. The table is based off of chemical reactivity. That chemical reactivity is based on electrons, but the table's shape came out of chemical reactivity. Columns have similar reactivity.
There was a question like that on the quiz, and I remember is one of the answers on the multiple choice is radioactivity. I clicked that one, but I remember it was not that one. So I wasn't really sure why it would be radioactivity.
I'm sorry, did you say radioactivity?
Yeah. Oh, you said yeah.
Reactivity has absolutely nothing to do with radiation. Not radioactivity. Mm-mm. Nope. There was an N there. When Mendeleev came up with the table, they didn't even know anything about radioactivity yet. They hadn't realized, it's pretty sad to say, they actually hadn't noticed that things were radioactive yet, even though they were doing a ridiculous amount of mining. They came across it a lot, and people died of weird deaths. They just didn't realize why they were dying of weird deaths and whatnot. Okay, how many energy levels exist, and how do they relate to the table?
7.
7, and 7 rows on the table. Okay, how many sublevels exist? 7. And so S, P, D, F, G, H, and I. And which ones do we not really need?
G, H, I.
We don't really need G, H, and I, only because we don't have atoms big enough to fill those sublevels. No other reason. I mean, they still exist. They're still there. You can still excite an electron up to those spots. It's just that they're not going to sit there when they're in their ground state. How many electrons fit in an orbital?
2.
2. Just 2 electrons per orbital. And which sublevels are found in the second energy level and why?
S and P.
S and P and the Y.
Because they're the first 2 sublevels.
Energy levels have their number of sublevels. So if I'm looking at energy level 4, there are 4 sublevels in energy level 4. Energy level 1 only has 1 sublevel in it. So whatever number's energy level is, that's the number of sublevels that that thing can fit. How about, okay, how about 4? How many can fit there? How many electrons can fit in the 4th energy level?
32.
Is it 32? There's an S, a P, a D, and an F. There are 2 electrons that can fit in the S sublevel because it's 1 orbital. There's really? Sorry, I don't know what the heck that was.
Sometimes those touch screens, I think static electricity makes them just start.
You're totally right. I'm wearing wool and not wool. 6 electrons can fit in the P sublevel. 10 electrons can fit in the D. And 14. So whatever that adds up to, which is what? 32. Yo.
So it wouldn't just be 14 because you'd add all of them?
I asked about the 4th energy level itself, not the 4th sublevel.
Oh, that's fine. Okay.
So all of the sublevels that are inside that 4th energy level is what we were trying to add up. All right, so N's electron configuration. So 1s2, 2s2, 2p3? 1, 2, 3. Okay. And sulfurs, 1s2, 2s2, 2p6, 3s2, 3p4. You're gonna need to write this whole thing out if asked a question like this. You can't write the shorthand one unless you were asked to write the shorthand one. So iron, Fe, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7, 1, 2, 3, 4, 5, no, 6. Is that the cursor, or is that an, oh, that is an I. All right, so iodine, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7, and we're at, no, we're at bromine, 4p6, 5s2, 4d10, and 5p5.
You got a 3D7 in there, is that 3D10?
Yeah, I don't know why I wrote 7. Thank you. And how could you quickly kind of determine if this, say any of these, but particularly the last one is correct? You can check out the last part, right? The 5p5. So go down to the 5th row, go to the P block, and go over to the 5th column and see if you hit iodine. You could also add up all the superscripts, right?
Yeah, okay, the atomic.
2, 2, 6, 2, 6, 2, 2, 6, 2, 10, and the 5, and then go up there, and does that equal the same 53 for the proton electron number it is for iodine? If it's not the same number, then something's wrong. All right. Hund Rule? Which one was Hund's Rule? It isn't E, isn't it? So Hund's rule is the 2 electrons in that p sublevel that are in individual orbitals. So I make sure I put an electron in each of the orbitals in a particular sublevel individually before I start doubling them up. Why are they getting thrown into separate orbitals? They have the same charge, so they're repelling each other, and the orbitals are all at the same energy, so it doesn't matter which one you put it into. They're no further away, if we're talking about using that merry-go-round example. They're all at the same distance away from the merry-go-round, so it doesn't really matter if they're right next to each other or if on the opposite side of the merry-go-round. So they're not going to want to be next to each other. And then the Pauli's principle?
Electrons have spin, they spin opposite each other in an orbital.
So all the up-downness is due to the fact that they're spinning, and they want their magnetic fields to attract, even though their electric fields are pushing away from each other. Heisenberg's uncertainty principle. What's up with that?
You can't photograph an atom because the light would move the atom, therefore it wouldn't be there to take a picture of it.
That's definitely the result. The actual definition is may not know position and momentum of an You can never know where it is and how fast it's going at the same time. You can know where it is, but you don't get to know how fast it's going, or you can know how fast it's going, but you don't get to know where it is. And the result of that is observation of a subatomic particle moves the subatomic particle. It adds energy to the subatomic particle. What is the shorthand notation? Noble gas configuration, stop at a noble gas. So there's no reacting for those noble gas electrons. So if the atom that I'm looking at now has the same electron configuration as a noble gas, all of those electrons are not reactable. They will not react. So in essence, what are elements trying to do to their reactivity? Somebody else said it over here. They're trying to stabilize themselves. They want to be like a noble gas. They want to be not reactive. They'll go from reactive to not reactive. They're trying to lose energy. They're trying to lose the ability to do anything. So we have titanium here. So 2. So then the last noble, if you look on the table, find titanium at 22, and you back off to the last noble gas, which is argon. So it would be titanium, and then argon in brackets. And then after argon, we're looking at 4s2, 3d2, and that's the whole thing. Which column is the halogen column? So it's either 7a or 17, depending on which of the column notation you're using. And uses for those guys? Okay, you could use it for lighting. What else? Disinfectants? Okay. That's probably the 2 major uses for those guys. What about the alkaline earths? Yeah, the alkaline earths. Which ones are those guys? 2A or 2. And why are they named? Mostly, what's up with that word right there? The water's pH goes up. So the alkalinity is an older term for base, and so when added to water, the basicity of the water goes up. It becomes more basic, or it becomes basic. Okay.